According to the definition of atomic physics, a photon is a particle with zero rest mass and zero electric charge. Its energy is purely kinetic. The photon would move, in a vacuum, at the speed of light, composing its particle nature. Now, let's try to translate these seemingly complex concepts. When one says that the photon's rest mass is null, it is understood that the photon only exists while it is in continuous and relative motion. As for its displacement in a vacuum, some difficulties arise. For example, a photon that was emitted by the star Sirius at this very moment would be retained for 8.6 years within its future light cone. As the future has not yet arrived, we cannot prove its absolute displacement in a vacuum. This would explain the fact that the photon is a particle with zero rest mass, since, for our point of view, it is never stationary. By the time the photon's velocity could be measured, we would already be in possession of the information it carries. That is, Sirius light would have already reached Earth, and we find ourselves, now, looking back in time. The future would have already passed over the present, following the scattering of the photon emitted by Sirius. The imaginary arrow of time that, as we know, would always point to our future, undergoes an apparent inversion, starting to point to our past. Once we know the speed of 300,000 kilometers per second, attributed to light by precise measurements, based on some form of remote tracking, we usually extrapolate this data into the star's future cone of light. It is as if the future were treated, by us, as if it were an inverse image of our own past. This leads us to conclude that Sirius light is arriving from the past of the heavenly vault, not the future. However, in the case of Sirius' abrupt death, it would continue to shine in the sky for another 8.6 years. A single photon carries, with it, all the information our brain needs to describe physical reality. However, the photon is only a means of transporting information, which shows us the real universe, as it was in remote times, not in real time. The photon is not reality itself. If physical reality were also linked to space, the two could not be accessed directly. That is, the photon would become the space messenger. This problem is related to the uncertainty principle. In 1928, Niels Bohr presented an experiment with a microscope to illustrate the uncertainty principle. Consider a measurement taken to determine the instantaneous location of a particle using a microscope. In such a measure, the particle needs to be illuminated because, after all, it is the quantity of light scattered by the particle that the microscopist sees. According to Heisenberg, the state of affairs, described by the uncertainty principle, is a direct result of quantization. The quantization of electromagnetic radiation requires that at least one unit of light, a quantum, be scattered across the particle, or that no light is scattered at all. The scattered light provides the interaction that must exist between the measuring instrument and the particle. This interaction disturbs the particle in an unavoidable and unpredictable way. The physics description of the uncertainty principle shows that particles cannot be seen directly. Quantum formation is a total mystery to us, as it takes no measurable time. For the point of view of the quantum system operator, the photon appears ready and in continuous motion in the form of light scattered by the particle. This light contains all the information we need to interact with matter. When talking about the quantum level, the world of atoms and molecules, there is an incompatibility involving the forces that act there, in relation to those observed on the astronomical scale. This incompatibility has to be apparent, as the universe is the same on all its levels. This has spurred researchers to try to craft a unified theory. Newton considered that all infinities are equal, which was recorded in a letter sent to Bentley. Any and all theory that seeks to unify infinitudes will only succeed if it takes into account the standpoint of the isolated observer. This becomes evident when one realizes that both atomic structure and distant galaxies rely on the same form of remote tracking of light photons. This is what Bohr's experiment with the microscope, cited previously, shows us. On the other hand, when you used a powerful telescope to observe the Andromeda galaxy, you would still need to rely on scattered light at your position. If its light weren't already here, the galaxy could not be seen at the other end of the telescope. That is, it would not be relevant to consider the time and distances previously covered by the photons of light. When analyzing the timeless nature of the quantum of energy represented by the photon of light, one has the impression that the light would have been previously retained in some mysterious place in space, which could not be accessed directly. This mysterious place would be completely obscured when the light hit the particle and spread. Before that, the particle could not be seen. This apparent spatial displacement leaves, in our brain, the impression that the particle is always seen late and out of its true position. Physicists suggest that an electron from a metal plate would take a long time to make its quantum leap because it would suck energy from the plate. However, it was not possible to measure any time interval between the collision of the quantum with the electron and the scattering of light. To everyone's surprise, both appear simultaneously. As can be seen, the scattered photon is, simultaneously, a unit of light and time. A quantum of energy of a purely kinetic nature. Our brain translates the uncertainty created by the photon into a form of veiled retention of time. All forms of energy that can be measured are quantized or packaged in the form of a photon. Thus, there could not be a so-called dark energy, because, when it could be measured, it would lose this condition. Quantization, in some mysterious way, would implode the time before the photon scatters. It is worth remembering that it would be this light that would allow us to register, in an exclusive way, the position or speed of the illuminated particle. It becomes impossible for the observer to scale the time before the photon scatters. It would not matter if the metals of time were minimal on the atomic scale or tending to infinity on the astronomical scale. As all the events taking place in the celestial vault, including space itself, were described by light or by cosmic radiation, the harmonic behavior of light could not be neglected. It would act similarly to a spring. When it was stretched, we would have the first phase of harmonic movement. The second phase would be its contraction. These two phases are mutually exclusive, because, if you see the spring stretching, you cannot see it contracting simultaneously. In a risky way, science borrowed the behavior of light to define that of space itself. This has a logical explanation. If you need light to see the stars, and the nature of the photons used was purely kinetic, the behavior of light and space merge into one thing. This is because space would have been dislodged in an unrecordable way by the timelessness of the photon's quantization phase. That is, space would have virtually flattened over its original 2 dimensions. Without time, there is no measurable movement, and you, then, have to wait for the arrival of the photon. In other words, the photon could only move after the inversion in the direction of the arrow of time next to us. From our point of view, light appears to be replacing space, or acting as its messenger. When scattered, the light waves appear to be continuous, ignoring the photon's packing phase. Due to its timelessness, the quantization phase cannot be measured directly. Therefore, according to the precepts of physics, what cannot be measured does not exist. It can be seen that the uncertainty of position or velocity related to the quantization of the photon would be supporting the functioning of our memory. It is very difficult to conceive that this memory could be functioning discontinuously, with the uncertainty of position or velocity being managed by a single photon of light. But that's what happens.